Hi geographers, welcome to this video about statistical skills. In this video we're going to be examining how we go about completing and using the Spearman's rank test on some sets of data. It's worth us starting off by outlining what the Spearman's rank correlation coefficient actually is and how it works. We use this test to test the strength and the direction, as in whether it's positive or negative, of a relationship between two variables. So the most common situation where you would use a Spearman's rank correlation test is perhaps after you have plotted some data onto a scatter graph. We're going to have a look at some examples in this video, but a really simple one that we could think of is maybe distance along a river and the discharge of a river. We could plot how those two variables change and we could see or not whether there is a relationship or a correlation between those two. If we drew a scatter graph and it appeared, maybe because we'd put a line of best fit on that scatter graph and there appeared to be a bit of a correlation or a bit of a relationship, then we could use the Spearman's rank test to help us firstly assign a number to the strength of that relationship, so get an indication of how well correlated the two variables are, and also use it to test for the likelihood that that relationship could be a random one. So if we deal with the first point about the strength of the relationship, that relates to the calculation that we will do, and the result of our calculation will give us a number between +1 and -1. And the closer our result is to 1 or -1, the stronger that relationship is. So if we got a value that was very close to 1, let's say kind of 0.8 or above, then we could think about that as being a strong positive correlation. Okay, so on a scatter graph, that our points might look something like this. Okay, where as one variable increases, another decreases. If we had a value that was closer to -1, let's say we had a value of -0.8, then that's still going to be a strong correlation, but it's going to be a strong negative correlation. And again, if we think about what that would look like on a scatter graph, that would be that as one variable increases, the other decreases. So our points might look a little bit more like this. Any value that is quite close to 0, and normally we're kind of taking the halfway point, so 0.5 downwards or 0.5 upwards, we can think about that as being no correlation. So no significant relationship between the two. Anywhere in between the two, we're thinking about that as being a weak positive or weak negative correlation. So you have to think carefully about the result, and how close it is to 1 or -1 is basically telling us the strength of the relationship. It's very unlikely that we will get a result that is exactly 1 or -1. It's very often that we get a decimal of 0 point something. What we then have to do, and I'll explain a little bit more about this later on, is test that value for significance. What this means is we have to compare it to some values in a table, and that will give us the likelihood that that relationship has occurred at random or by chance. We'll see some examples of that later on, but we have to be aware that sometimes correlations exist and they are purely at random, and we need to know the likelihood that our relationship could be a random one, and that helps to give us some confidence in our results. So we often think about these critical values as being kind of confidence levels. How certain can we be that our result shows what we think it's showing? Okay, so in terms of how we go about completing a Spearman's rank test, again, as we've done in previous videos, I've just given you the sort of steps here because it's handy to have them all in one place. But we are going to go through a little worked example together in a moment. A couple of things to note. Firstly, that actually most of the Spearman's rank calculation is done in a table. So by laying out our data properly in a table, then we can actually do most of the calculation in the right way. As the name suggests, Spearman's rank involves ranking the data sets. So we're numbering them in terms of their relative ranks, and we do this from highest to lowest. Okay, so we rank the largest value 1, the second largest 2, and so on. Okay, and we go down until we get to the smallest value, and that will have our lowest rank depending on how many observations we've got. And we do that for both sets of measurements. So we rank one of our variables, like distance downstream, and we rank our other variable, like river discharge, and then we can work out the differences between those ranks. Important thing to mention here is that if two variables have the same score, let's say we had 2 points along our river's course that had the same discharge, then we give a mean rank or an average rank for those. I'm going to model that to you in a second, but just wanted to point that out for you. It's a little bit like imagining two people finishing with the same time in a race. They might be joint first or joint second. The same sort of principle applies here. That can happen where you have more than 2, maybe 3, 4, 5 variables that all occupy the same rank. So it can get a little bit complicated, but we'll have a look at that in a minute. As I said a moment ago, once we've got the ranks, we can find the difference between the ranks. That's indicated by this letter D. We square that value to give us this D squared, and then we sum up all of those D squared, and that gives us this figure here, the sum of D squared, which actually gives us the most difficult part of this equation here, 6 times the sum of D squared. Well, when we've worked that out, we can easily multiply it by 6. N, in this case, as with all of our statistical examples, refers to the number of observations that we've got, so maybe the number of points that we visited along a river. So once we've worked out the sum of D squared, we can simply put that into the calculation, substitute the other numbers in, and then we have got our result. Just want to give you a little bit of an example now of what I mean about those rankings. So as we said, we always rank from highest to lowest. So imagine here I've got some data for the rainfall, and I wanted to rank these observations from highest to lowest. Well, 964, that's going to be my highest, so that's going to get a rank of 1. My next highest, 840, that's going to get a rank of 2. My next highest is 735, and you'll notice I've got 2 of those. Now, what I don't do is rank them both 3. I need to give a mean rank here. So the next ranks that I'm going to use are 3 and 4, because I've used 1 and 2. So the next ranks I've got available to me are 3 and 4. Now, if I took an average of those two, if I did 3 plus 4 divided by 2, that would give me 3.5. So both of these values, both of these observations get ranked 3.5. I then come to my next highest value, okay, which is 550. Now, I don't rank this 4 because I've used 4 here in my calculation. So I would rank that as 5. 1, 2, 3.5, 3.5 and 5. That's because I've used 3 and 4 in my calculation to get these two numbers here. I then carry on down that list, so my next highest would get a rank of 6, my next highest would get a rank of 7, and my next highest would get a rank of 8. Okay. What I'd like you to do, pause the video at this point and see if you can have a go at working out how you would rank these variables here. So we've got some temperature observations here. You'll notice there are some similar numbers. So see if you can work out how you would rank those bits of data. Okay, so again, we're going to go from highest to lowest. So our highest value of 32, that's going to get a rank of 1. Our next highest value of 30 is going to get a rank of 2. Our next highest value is 27. Now we've got 3 observations here which have 27. We've got 1, 2, 3. So the next ranks we've got available to us are 3 and 4 and 5. we would use 3, 4 and 5 in our calculations for this, and we would divide that by 3. Essentially, that gives us the middle number here. Okay, so we would rank all of those as 4. So now we have 1, 2, 4, 4, 4. The next value is 25, which I'm going to rank as 6, okay, because I've used 3, 4 and 5 in this calculation. I can then finish that off by ranking that one 7 and that one 8. Well done if you managed to get those in the right order. So that explains there how we go about giving this mean rank. If 2 or more observations have the same value, like 27 here, okay, or 735 here, we are giving a mean or an average rank. That doesn't always mean it's going to end in a 0.5. If you have 2 observations, then it will. But if you have 3, then it would be a whole number. Okay, so you need to think carefully about how you're doing this. One thing I find quite handy to do is think about how many observations I've got, so in this case 8, and actually write the numbers 1 to 8 on a scrap piece of paper, and then cross them off as I'm doing my ranking. And then when I get to this sort of situation here, I know which ranks I've got available to me, and then I can cross them off as I go along. So that might be a little tip for you to help you with the ranking, because if you get the ranking wrong, the rest of your calculation isn't going to make sense either. Now, on to what I was saying earlier about this idea about a relationship occurring at random. So here's a couple of silly examples of correlations that fit together even though they actually have no relation to one another. So this person here has looked at the number of people who drowned by falling into a swimming pool in each year, and the number of films that the actor Nicolas Cage appeared in. And if you were to do a Spearman's rank correlation test on those things, you'd get a value of 0.66. Okay, so actually a fairly clear correlation between those two things. When the number of Nicolas Cage films are higher, the number of people who drown in swimming pools is higher. So that's clearly a random relationship. There's no connection between those things, yet when you do a statistical test using those 2 bits of data, they do actually fit together relatively closely. Another example here, an even stronger correlation. This actually fits together with a Spearman's rank value of 0.94, so a really strong positive correlation here. And this is looking at the relationship between the amount of cheese people eat per capita and the number of people who die by becoming entangled in their bed sheets. Again, another clearly random relationship that has no bearing to reality at all. These two things just happen by chance to fit together. And we need to know, anytime that we do a statistical test, what the likelihood is that our result could be one of these random relationships. Okay, and this is where some things that are called critical values come into play. So we have to go through this process of testing for significance, okay, or significance testing. So we can only do this once we've calculated our Spearman's rank value, and we need to compare that value to the critical values which are set out in a table. That table is always the same. You can look up examples of it online. In an exam context, you would always be given the critical values, and it's simply a case of comparing your result to those values. And two things can happen. Either your result will be higher or greater than the critical value, in which case that's great because our hypothesis can be accepted. We can jump for joy that we can accept our hypothesis, and we can accept it with either a 95 or 99% confidence that the result is not random. We can never be 100% confident because there's always a chance that those random relationships occur, as we've just seen, but we can either be 95 or 99% confident. The reason that there's two numbers here, two different confidence levels, is because in the table there will be more than one number. So you can look and see which number your result is higher than. I like to think about this a little bit like someone doing the high jump. Okay, and the bar for that high jump is set at a certain level. Okay, let's call it 0.6. And if your result is higher than that, then that's great. You're over the bar, and that would be a successful jump, wouldn't it? Spearman's rank works in exactly the same way. The only difference being here, there are 2 bars. Okay, and the lower one is the 95%, or sometimes abbreviated as the 0.05 level. We'll see why that is in a minute. And then there's a higher one which represents 99% confidence. So if you're above this 95% level, you can be 95% confident. And if you were even higher than that and you're over the 99% level, then you could be 99% confident. Sometimes you'll even see what's called a 0.001 level, and that's the same as being 99.9% confident in your result. Okay, the most common ones you come across will be these 2 here. If, however, like it says down here, the Spearman's rank value is less than the critical value, let's say you only jumped this high, you can't be above that 95% level. You're not above that, and therefore you have to reject your hypothesis, because there's too much of a likelihood that even if you've got a fairly strong relationship, that result could be a random one. So here's an example on the right hand side of that table that I was just talking about. In this case, n represents the number of observations. So if you went to 10 sites along a river, you'd be looking at this row here. If you went to 18 sites along a river, you'd be looking at this row here. So although there are lots of numbers in the table, actually at any one point you're only looking at 2 of them. You're only looking at the 2 that relate to the number of observations that you have. Now you'll notice there's also 2 columns. This 0.05, okay, and the 0.01, both of these represent the likelihood that the result is random. So 0.05 is the same as saying 5%. Yeah, that decimal 0.05 is the same as the percentage 5%. So if there's a 5% chance that it is a random relationship, by the same token, there's a 95% chance that it's not random. So that's where we get that idea that I was talking about a moment ago about confidence. Okay, so you can be 95% confident because there's a 5% chance that it could be random. 0.01 is the same as 1%. Okay, so if there's a 1% chance that it's random, there's a 99% chance that it's not. So that's how those 2 numbers relate to this idea of confidence. Now, a couple of things you'll notice as well. The 0.05 value is always lower than the 0.01. So all of these numbers in this right-hand column are higher than the ones in the corresponding left-hand column. Okay, and that's because in order to be more confident, you'd need a higher result. So that again links to that idea, as I was saying earlier, about that person doing the high jump. Okay. This graph on the left-hand side isn't one that you need to worry about being able to interpret, but it just gives you the same picture again, that bar for the 1% or 0.01 level is always higher than this bar for the 5% level. Okay, and the 0.01, or 99.9% confidence is even higher again. So the more confident you are, the higher your result needs to be. And also, the more observations that you make, the lower that bar gets. So you'll notice this as well. As we go down this list, 0.64, 0.61, 0.54, all the way down to 0.45. the number of observations you make will determine how high your bar will be. Okay, so this stands to reason, doesn't it? If you just measured 10 things and you found a pattern, there's more chance that it's random than if you measured 20 things or 100 things and you still found the same pattern. The more things that you measure, the less chance there is that that random relationship is going to be present. So that's why those numbers get lower as we go down that list, and that's why the 0.01 level is higher than the 0.05 level, okay, because this is a higher level of confidence than this one. Let's put this into action then. So the first thing we're going to have a look at is this example of an investigation into a country's level of development and child mortality rates. First thing you would always do before you'd even bother doing a Spearman's rank calculation is to draw a scatter graph. So this student here has drawn a scatter graph plotting the Human Development Index, okay, that's what HDI stands for, and the child mortality rate. They've plotted those two figures onto a scatter graph for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 countries here. And they've got a line of best fit on that graph. And there definitely appears to be a bit of a correlation there, doesn't there? A negative correlation that as a country gets more developed and its Human Development Index increases, child mortality rates come down. Now, the next thing that you would have to do is actually establish that idea as a hypothesis. So sometimes you will see a hypothesis referred to with this abbreviation here, H1. Okay, so our hypothesis, our statement that we're trying to prove, says as Human Development Index increases, child mortality rates decrease. That's what the pattern is showing on the graph. So if we do our calculation and it turns out to be significant, then we can accept that hypothesis. If, however, we do a calculation and it turns out that it's not at a high enough level, we can't be confident enough in our result, then we would have to accept the null hypothesis, which is sometimes abbreviated as H0. Okay? The null hypothesis is always that there's no relationship between A and B. In this case, no significant relationship between Human Development Index and child mortality. So even though we can see a pattern on this scatter graph, that's not enough on its own for us to actually be confident that that result exists. We have to use statistics to give us a little bit of objective confidence in that result. So let's have a go at working through this example together. So as you can see, we've got our countries listed down the left-hand side, and we've got the corresponding bits of data, the Human Development Index for each of those countries and the child mortality for each of those countries. What we need to do is to go down our list and rank all of these numbers from highest to lowest. So you have to be really careful, and it's worth taking your time doing this. So we have to look for our highest value, which is actually this one here for Germany, 0.947. So that gets a rank of 1. The next highest is 0.944 for Australia, so that gets a rank of 2. The next highest is the UK, which gets rank 3. And the next highest is Japan, so that gets rank 4. Now I'm just going to whiz down the list and rank all of these in the right order.
Move it. I like to move it, move it. I like to move it, move it. I like to move it, move it. You like to.
So there we go, we've ranked the data for the Human Development Index from highest, which is Germany, all the way down to the lowest value for Chad. Next thing we need to do is rank the data for child mortality. So again, we're going to do this from highest to lowest, but notice along the way that we have got some values that are the same here. So for example, India and South Africa both have the same value, so we need to be careful when we get to those. So our first and highest value is going to be Chad, which is ranked 1. Our second highest, Cameroon, will get a rank of 2. Our next highest is in Zimbabwe, which will get a rank of 3. Our next highest is for South Africa and India that I mentioned a moment ago. So again, we've used 1, 2, 3. The next ranks available to us are 4 and 5. So we would rank both of these as 4.5. And then the next highest value will get a rank of 6, which goes to Mexico. So we'll rank that as 6.
And the 7th highest is Brazil. Next highest is Russia. And then the next highest after that is France. So that gets a rank of 9. And then following that, the UK gets a rank of 10.
Then we get to the situation where Australia and Germany actually have the same infant mortality rates or child mortality rates. So again, we need to think about which ranks are available to us. The next ranks we would use are 11 and 12. So both of these will get a rank of 11.5. Our next highest will get a rank of 13, which is going to be the Czech Republic. And then finally, our highest rank, Japan, gets a rank of 14. The next thing we need to do then is to work out this column here representing D, which stands for the difference, or the difference between the ranks. So not the difference between the data itself, but the difference between these two numbers. The general rule of thumb is you do the first rank minus the second one. So if we did 2 minus 11.5, we would get minus 9.5. What's quite a good idea to do when you're working this out on your calculator is to then hit the squared button so we can get this column here, which is the difference squared. So minus 9.5, if we square that, we get 90.25. Remember that when we square a negative number, the negative sign disappears. If your calculator still has it on there, just ignore it and put the number in without the negative symbol. So minus 9.5. Again here, 9 minus 7 gives us 2. 2 squared is 4. Next one, 13 minus 2 is 11. And we square that to get 121. I'm just going to carry on now and just whiz down and put those numbers in the columns. So there we have the difference between our ranks in this column and then the squared value in the final column. Last thing we need to do is add all of those numbers up. So if we get our calculators out and do that, we would get a value of 867. What we can now do is take this number and substitute it into our Spearman's rank equation. So it says here RS equals 1 minus 6 times the sum of D squared. So 6 times 867 divided by n cubed minus n. And n is always the number of observations or number of samples that we've got. In this case, the number of countries, which is 14. So that would be 14 cubed minus 14. We can take that on a stage then, so we can think about that is the same as doing 1 minus 5202 divided by 2730. So again, we can work out that bit in the brackets is 1.905, which means our overall value is minus 0.91, rounded to 2 decimal places. So that is the value of our Spearman's rank calculation. We know we've done it correctly because we've got a value that's between 1 and -1. If we got something else, we would start to question it. Always remember to do 1 minus this part of the answer. Sometimes people get hung up with doing the bit in brackets and then they get a number that is between 1 or -1 here and they think they've got it and they've forgotten to do 1 minus that. So our result of 0.91, that tells us one thing, that is a strong negative correlation. However, we also need to think about the likelihood that that result could be a random one and how confident we can be in our result. So this takes us back to our significance levels then. So if we remember, our result for Spearman's rank was minus 0.91. We want to be having a look down this table at this column, at this row here for 14, because we had 14 countries. So in order for us to be 95% confident, our result would have to be higher than 0.54. Now what we have to remember at this point is that we ignore the negative value. We imagine that that negative sign isn't there. So we're just thinking about 0.91 in relation to these numbers in the table. So 0.91 is higher than 0.54, so we can definitely be 95% confident. And this value here represents 99% confident. And again, 0.91 is higher than 0.66. So as a result of that, we can accept our hypothesis. Okay, we can be very confident, okay, 99% confident that as human development index increases, child mortality rates decrease. Just as an example, if we had a value, let's say our result wasn't 0.91 at all, let's say it was 0.61. Okay, in this case, we could be 95% confident because it's higher than that value, but we wouldn't be able to be 99% confident because it isn't higher than this one. Now that wouldn't matter because we could still accept our hypothesis just with 95% confidence rather than 99. If, let's say, our result was a bit lower and it was 0.51, then it wouldn't be higher than this value, so we'd have to accept our null hypothesis instead. Anything less than this 95% level is not good enough for us to be able to accept our hypothesis. It has to be 95 or above. In this case, we're well above that 0.66 level, so our result is definitely significant and we can be 99% confident that that result is not a random one. Okay, over to you then. You're going to have a go at completing an example now which looks at the level of deprivation in areas of Tower Hamlets in London. So Tower Hamlets is a borough in London, and a student wanted to explore education and employment data to see if there is a relationship between the two things. So they collected dates. So they collected data from 19 wards, 19 areas of Tower Hamlets, and they measured two things: the rates of unemployment and the rates of adults with no qualifications. So they're looking to see if there is a link between those two things. The data that they collected is here. So you can see the names of those different areas. You can see the number of adults per thousand with no qualifications, and you can see the unemployment rate per thousand here. What I want you to do is work your way through this example, remembering that the first thing you're going to need to do is to establish a hypothesis and a null hypothesis. So a H1 and a H0. You're then going to need to calculate the result, which will involve you filling in all of the data in the table and then taking this number and putting it into the equation here. And then you're going to need to do that significance testing and to check the confidence level of your result. Remembering that in this case there are 19 wards, so we are looking at this row of the table here. Pause the video and on your worksheet have a go at that, and then we will check our answers. Okay, so in terms of your answers to this task then, here is the data filled into that table. First thing to check, did you get your sum of d squared to be 289.5? If you didn't, then you'll have done something wrong in terms of the rankings or your calculations of the differences and the differences squared. So just double check. If you got that answer, great. If you didn't, just have a look at where you went wrong with your rankings. So then what you needed to do was to put that data into the equation. So Spearman's rank is 1 minus 6 times the sum of d squared. So 6 times 289.5 is 1737 divided by 19 cubed minus 19, n cubed minus n, which is 6840. Well done if you got that far. So that is the same as doing 1 minus 0.254, okay, which gives us an answer of 0.746. We might have just put 0.75. That's absolutely fine if you've given it to 2 decimal places. Final thing we needed to do was to have a look at this row of our table because we have 19 wards, 95% level, 99% level. We're above this value, so we can be 95% confident, and we're above this value here, so we can be 99% confident when we accept our hypothesis that a high rate of adults with no qualifications results in a higher rate of unemployment. Well done if you managed to get all of those rankings correct in the table. Well done if you got your calculations correct, and well done also if you managed to test that properly for significance. So that concludes the video about the Spearman's rank test. It's a very useful test in geography when we're trying to look for the links and relationships between 2 variables. We can apply it to lots of different types of data, both human and physical geography. And really the only limiting factor is having enough observations to be able to do the test. If you've only got 8 or 9 samples, then that's going to be quite hard to do a Spearman's rank calculation. But anything above that, 10, 20, even up to hundreds of samples, we can use this test to maximum effect.